And now what happens if we were to multiply by a scalar? So what happens if we do scalar multiplication kind of things? Well, if we multiply our vector by a scalar, then again, what happens to the components? Okay. So let's go in and state that, vector D, because I already use C here, let's say it's twice A. Something nice and simple. Okay, so we'll start off with our vector A like we had it before. And then I'm going to say vector D is just twice vector A. And we're going to try to, figure out what's going to happen to the components. Okay. That's our 10 meters, 30 degrees north of east. AX and AY, nice little component triangle, like yay. Now, if vector D is twice vector A, then it points in the same direction. It's just twice as long. So being twice A, this would be 20 meters. Notice that the angle is still 30 degrees. And what we want to talk about is, well, what happens to the components? Dang it. dy. The question is, how are dy and dx related to ay and ax? Well, if we look at our component triangles, the purple and blue one versus the red and green one, how are those triangles related? What's the relationship there? Okay. It is the same direction. There are different magnitudes, but what about the triangles? How are they related? How are our component triangles related to one another? Yeah, all the angles are the corresponding angles are the same. These are 30s, these are 90s, these would be 60s. So what that means is that the component triangles are the same shape, but they're different sizes. And so these are referred to as being similar triangles. So with a similar triangle, what you get is that corresponding angles are equal, and then corresponding sides are proportional. And so what happens is that if we double the hypotenuse, then what you get is you double the sides. You double the components. And so then what we'll have here is that our dx will be twice ax, and dy will be twice ay. And so then this gives us our rule, is that if you multiply a vector by a scalar, then you multiply the components by that same scalar. So whatever we do to the vector, we end up doing to the components. And so this is the big rule type of things. All right, and so then if we wanted to go in and calculate, what did we do? A plus 2b minus c. So we want to calculate, but we want to do this in terms of components. Then, and let me just do x's and y's. So then I get ax I hat plus ay in the j hat direction, plus 2 times, and then b would be bx in the I hat plus by in the j hat. And I'm going to subtract off c, and c would be cx in the I hat plus cy in the j hat. And then again, what we'll do is we'll go in and collect up all the I hat kind of terms. We do need to be careful to make sure that we distribute in through all of our pieces. And so then what we'll get is that this will be ax, and this will be plus 2 times bx, and this will be minus cx, and this is all in the I hat. And then I can collect up the j hat terms similarly, just like we saw before. And I get that this will be ray plus 2 times by minus cy, and these are all in the j hat direction. So whatever we do to the vectors, you do to the components. And you do x's with x's, y's with y's. We could then recombine. So then this will be the x component of r, plus this will be the y component of the resultant vector. And we take these two pieces and fold them back together to get the resultant vector itself.